Today we are performing a diagnostic anatomy of productivity loss. So looking at the slide, you see a glowing orange cross-section of a furnace with a bright blue gas column rising through the center. This represents a delicate balance between the burden descent and the gas ascent. By the end of this session, you will gain three key deliverables. First, the mathematical production equation that dictate your tonnage limits. Second, a deep understanding of the two 8 hours cooling spiral that lead to hard chilling. And finally, an expert diagnostic matrix for real-time corrective action. We are moving beyond guesswork and into a rigorous three-pillar root cause analysis: aerodynamics, thermodynamics, and fluid dynamics. To understand why these pillars matter, we must first look at the governing equation that link wind volume to the reductant rate. Now, coming to the slide, so look at the central formula. Production is proportional to blast volume. The numerator in the blue box divided by the specific reductant rate in the orange box. The so what here is absolute. You cannot just increase the numerator without consequences. If your furnace requires more coke per ton of hot metal because of poor reduction kinetics, your burden descent slows down and your output drop regardless of how much wind you try to force in. Notice the three tabs at the bottom: aerodynamics, thermodynamics, and fluid dynamics. These are the gates. If you hit the ceiling in aerodynamics or fall into the endothermic trap of thermodynamics, the denominator spikes, the descent stalls, and your productivity evaporates. We do not just blow wind, we engineer the furnace's ability to accept that wind. The most immediate gate we hit is the physical limit of the gas velocity, known as aerodynamic breaking point. So let's look at the physics of the breaking point. On the left, the graph shows the blast pressure curving sharply upward against the production volume. There is a red dashed line that is your limit. Above this, the furnace is no longer stable. To double your gas velocity, your pressure must increase by a factor of 4. Now look at the resistance box on the right. Our ferrous burden, the sinter and the pellet, has 4 to 5 times the gas resistance of coke. We are talking about a harmonic mean size of 14 mm for sinter versus 40 mm for coke. The operational impact is clear. When you operate too close to the red line, you deteriorate burden descent. The only immediate corrective action is cutting blast volume, which directly slashes your production and increase your total plant cost. This resistance is not just about the particle size, it is about the fines that can lead to total void blockage. And our next slide is going to address exactly the same thing. So this is what the bad look like under a microscope. So look at the ideal state on the left: clean grayish spheres with thick blue arrows flowing smoothly through the gaps. That's the high permeability. Now look at the failure state on the right. Those small red particles are fines less than 5 mm in size. They act like sand in a drain, creating voidage blockage. Follow the blue arrow now. They are forced to the wall. This is the channeling. The so what is in the data box: a sudden drop in the gas utilization from 49 down to 36%. So when gas channels to the wall, it doesn't reduce the ore. This leads to a spiking stiff temperature and unreduced burden descending into the hearth. You are not just losing efficiency, you are physically attacking your furnace lining and setting the stage for a thermal collapse. When that unreduced ore hits the high temperature zones, we leave the world of aerodynamics and enter the thermodynamic trap. So, coming to the direct reduction trap, which is related to thermodynamic trap, we need to talk about the balance of reduction. So, look at the scale visual in the center. On the left, in the light of blue box, is indirect gas reduction. It's exothermic, it generates heat, and it's our best friend. On the right, highlighted in the fine orange, is the direct reduction trap. This happens when unprepared ore hits the 1200 degrees centigrade cohesive zone. This reaction is endothermic. It consumes massive amount of heat. The orange arrow pointing down on the right represents severe heat loss. The bottom line is the direct reduction robs the furnace of its energy. To compensate, you have to consume extra coke, which strips away your overall energy efficiency of the furnace and forces the reductant rate denominator in our equation to skyrocket. If you don't catch this direct reduction trap early, you enter a self-reinforcing failure mode called cooling spirals. So coming to address this cooling spiral, our next slide is all about that. So this is the most dangerous cycle in the iron making. Follow the circular blue arrow starting at the top. It begins with a trigger, unprepared ore reaching the high temperature zone. This leads to step 2, a direct reduction spike. So look at the diagnostic markers in the center box. You will see hot metal silicon dropping from 0.43 to 0.20. By step 3, the reaction has consumed so much heat that you have a thermal deficit. Now here is the counter intuitive part, that is step 4 is accretion. So because you are missing coke in the heart, the burden actually descends faster, giving the ore even less time to prepare. This is the cooling spiral. In a matter of hours, your furnace moves from a productive state to a critical thermal emergency where the hearth is no longer capable of maintaining liquid temperature. If this thermal deficit is not corrected, the internal structure of the furnace physically fails, leading to hanging and slipping. So coming to our next slide, which discuss on this hanging and slipping and the cohesive zone. So when thermodynamic fails, the physical structure collapses. So look at the three cross sections of the furnace. In panel 1, hanging a breeze forms in the cohesive zone represented by that thick red mass blocking the burden. In panel 2, the gas continues also to burn a void underneath that breeze. Finally, look at panel 3. The bridge fails and the layer structure is destroyed in a chaotic crash. The telemetry tells the story. The top gas temperature will spike over 1000 degrees centigrade as the hot gases bypass the fallen burden. Gas to ore contact is removed and the furnace chills instantly as unreduced material drops directly into the earth. This is not just an operational delay, it's a basically catastrophic event that can take days to recover from. So while the top of the furnace is sleeping, we must also monitor the fluid dynamics occurring at the very bottom. And our next slide which talks about that only. So let's look at the hearth. In this diagram, the left you see the yellow pool of liquid iron and slag. Look at the blue arrow pointing down, that's the weight of burden. Now look at the red arrow pointing up, the hydrostatic up thrust. If you have a poor cast house drainage, liquid level rises. As the liquid rise, they increase the upthrust on the cooked dead man and encroach on the tuer level. This is a hard choking. When this happens, gas flow is severely impacted, impeded also. The so what is an immediate emergency. Blast volume must be slashed to prevent blowing slag back into your blowpipe or causing a total tuer failure. You are essentially drowning your furnace in its own production because you cannot get the liquid out fast enough. To manage this complex interaction, we use a structured diagnostic matrix to bridge symptom to action. And our next slide is addressing on this expert diagnostic matrix. So this is your cheat sheet for the floor. Let's break down the 4 rows for channeling your telemetry source. Dropping the root cause is aerodynamics, and your action is adjusting burden distribution. For chilling, you see silicon dropping below 0.2%. This is the thermodynamics, and you need a cooked blank immediately. For hanging spikes and charging stops, you must drop the pressure to induce a controlled sleep. Finally, for hard choke, when the tuer go dark, the root cause is the fluid dynamics, and you must open the tap hole and slash the wind to a minimum. This matrix turns a room full of chaotic sensor into a clear, actionable directive. It's how we bridge the gap between knowing and acting before the furnace takes control of us. So mastering these individual pillars allow us to operate safely at the edge of chaos. And the in conclusion, the maximum productivity is not achieved by the simply blowing more wind. Look at this stable blueprint on the final side. It's basically a synthesis. Aerodynamics requires screen burden and stabilize. Thermodynamics require a stable cohesive zone and around 50%. And fluid dynamics require perfect cast house drainage to keep the deadman anchored. So we operate at the edge of chaos. The goal is to rigorously engineer these three limits so the furnace can safely accept the wind required for your production target. If you manage to mechanics, the tonnage will follow. And this is the strategy through which we could able to stabilize our furnace without any problem.